Welcome to the deep dive. Today, we're taking a really fascinating journey. We're looking into something that, yeah, it might sound complex at first, but it's absolutely critical for understanding how things work, from power plants to, well, even the air you're breathing.
Right. It underpins so much.
We're doing a deep dive into entropy analysis, basically working from a textbook chapter. And our mission today, it's really to unpack these core ideas, entropy, how it affects everyday things like compressors, turbines.
And crucially, how understanding this stuff can lead to, well, massive real-world savings, efficiency.
Exactly. Get ready for some aha moments, because this material, it really offers some incredible insights into optimizing systems, really rethinking energy use.
It does. Let's get into it.
Okay, so let's unpack this first idea, reversible steady flow work.
Right.
Think of these reversible processes as like the absolute gold standard, the theoretical best.
Like a perfect machine, no friction, no losses. It's the benchmark, the ideal we aim for, even if we can't quite hit it in reality.
And what's really interesting here is how this potential for work is tied so closely to the properties of the fluid itself.
Yeah, absolutely. For systems where fluids are flowing steadily, the maximum work you can possibly get out or the minimum you need to put in, it's really linked to this property called specific volume.
Okay, so specific volume. What does that actually mean for you in practical terms?
Well, it tells us that if you want to get the most work out of something, like, say, a turbine, you want the specific volume of that fluid to be as large as possible. Huge volume.
But if you want to put the least work in, like for a compressor that uses energy,
Then you want that specific volume to be as small as possible. Tiny volume.
it's like a fundamental lever you can pull in designing these systems.
It really is.
Okay.
And this is where the real-world impact just becomes kind of staggering. Our source gives us a great example. Compressing steam.
Ah, yeah, I saw that.
So if you compress saturated liquid steam, okay, it takes a certain amount of work, let's call it X.
Right.
But if you try to compress saturated vapor, steam, same starting pressure, same ending pressure, it takes over 500 times more work.
500 times. That's wild.
It's an astonishing difference, and it's purely down to the huge difference in specific volume between liquid and vapor.
Wow.
And that insight, that single point, is why modern steam power plants are designed the way they are. They're incredibly efficient because the pumps handle tiny liquid volumes.
Which costs very little energy.
Exactly.
Oh.
Very cheap, energy-wise. And then the turbines extract massive amounts of work from the expanding vapor with its enormous volume. It totally changes the design approach.
That 500 times more work fact, it really hammers home just how big a deal specific volume is, especially for things like compressors, the devices that use work.
Right.
So, okay, if we want to minimize that work input, put the least energy into a compressor, what are the actual strategies engineers use beyond just, aiming for that perfect reversible ideal?
Well, the most practical way, really, is to actively keep the specific volume of the gas as low as you can while you're compressing it.
Okay, keep the volume low during compression.
And since specific volume is directly tied to temperature.
Ah, right. So you need to keep the gas cool.
Exactly. Keep it as cool as possible during the compression process. That's the key practical lever.
Okay, and our source actually compares 3 different ways of doing this, or rather 3 types of compression based on how they handle temperature.
It does. And when you look at them on a graph, a pressure volume diagram, it becomes super clear.
So first, there's isentropic compression.
Right. Isentropic means it's adiabatic, no heat transfer in or out, and it's reversible. So basically no cooling happens.
And that results in?
The maximum possible work input. It's the least efficient in terms of work needed.
Okay. Then there's polytropic.
Polytropic involves some amount of cooling during the process. So it sits somewhere in the middle. It's better than isentropic, but not the absolute best.
And the best case.
That's isothermal compression. Isothermal means constant temperature. So this is the ideal, where you have maximum cooling, keeping the temperature steady the whole time.
And that requires
The minimum work input. That's the theoretical target for minimizing compressor energy use.
So constant temperature is the goal for minimum work. How do engineers actually achieve that cooling or get close to it in real systems? It sounds tricky.
Yeah, perfect isothermal compression is hard, but a very common and effective method is something called multi-stage compression with intercooling.
Multi-stage. Okay, so you break it up.
Exactly. Instead of doing one huge compression step, which gets really hot,
Right.
you do it in stages, maybe 2, 3, or more stages. And between each stage, you pass the gas through a heat exchanger.
An intercooler.
Precisely. An intercooler. Its job is just to cool the gas back down, ideally close to the initial temperature, before it goes into the next compression stage.
And doing that, breaking it up and cooling in between, that saves significant power, right?
Oh, absolutely. The total work saved could be really substantial.
Yeah.
And interestingly, to get the most savings, you typically want the pressure ratio across each stage to be the same.
Ah, okay. Balance stages.
Balance stages, yeah. And as you add more and more stages with intercooling, the total work you need gets closer and closer to that ideal isothermal minimum we talked about. It's a really powerful, practical strategy for efficiency.
Okay, so we've got these ideal benchmarks, reversible processes, isothermal compression. That sets the theoretical limit. But now let's talk reality. Real-world devices, turbines, compressors, nozzles. They aren't perfect. How do we measure how well they actually perform compared to their ideal selves?
Yeah, that's where the concept of isentropic efficiency comes in. It's a really critical parameter.
Isentropic efficiency, okay.
It basically quantifies how much the performance is degraded because of irreversibilities. Things like friction, turbulence, heat loss in the wrong places in actual devices.
So it's a comparison.
Exactly. It compares the actual performance you get to the performance you would get under ideal isentropic conditions. Remember, isentropic means adiabatic and reversible, no heat transfer, no imperfections. It's how we measure the real-world compromises.
And the way you calculate it, it actually changes a bit depending on what device you're looking at. That's important, right?
Yes, very important. The definition is slightly different. Let's take turbines first. They produce work.
Okay, turbines.
For turbines, the isentropic efficiency is the ratio of the actual work output you get.
What really comes out of the shaft.
Right. Compared to the ideal isentropic work output you could have gotten between the same inlet and exit pressures.
And good turbines are pretty efficient.
Oh, yeah. Large, well-designed ones can hit over 90% isentropic efficiency. They're remarkably good.
Okay, now what about devices that consume work, like compressors and pumps?
Right. Here the definition flips, in a way.
Yeah.
It's the ratio of the ideal isentropic work input.
The theoretical minimum needed.
Yes, the minimum work needed for an isentropic compression between the same pressures, compared to the actual work input you really have to supply.
Ah, so the ideal work is on top now.
Exactly, because actual compressors always need more work than the ideal case due to friction and heat generation. So the ideal work is smaller. Putting it on top keeps the efficiency less than 100%, which makes sense.
Got it. And typical efficiencies for those?
Good compressors, well-designed ones, usually operate in the 80 to 90% range. Pumps can be similar.
Okay, one more. Nozzles. Their job is to create high-speed flow kinetic energy.
Right, so for nozzles, the isentropic efficiency compares the actual kinetic energy the fluid has at the exit
How fast it's really going.
to the ideal kinetic energy it would have if the expansion through the nozzle were isentropic.
And nozzles, how efficient are they?
They're often surprisingly good, typically above 90%, and some can even exceed 95%. They're relatively simple devices hydrodynamically.
Interesting. So connecting this back, these efficiencies are less than 100% because of irreversibilities like friction. What's the consequence of that friction, say, in a nozzle, besides just lower velocity?
Well, a key implication, tying back to energy conservation, is that the energy loss due to friction doesn't just disappear. It gets converted into internal energy, basically heating up the fluid.
Ah, so the exit temperature is higher.
Exactly. The actual exit temperature of the fluid from a real nozzle will be higher than the temperature you'd get from an ideal isentropic expansion. It's a direct result of that energy degradation, converting potentially useful kinetic energy into less useful internal energy or heat. We see this everywhere.
Okay, so we've hit work, efficiency, ideal versus real. But underpinning all of this, the reason perfection is impossible, the reason systems degrade, is this fundamental property.
Entropy.
Yes, entropy. Often described, maybe slightly loosely, as a measure of disorder or randomness at a molecular level.
And the big rule, the second law of thermodynamics, basically says
Entropy can be created spontaneously, but it can never be destroyed. The total entropy of the universe, or any isolated system, is always increasing, or, at best, staying the same in an ideal reversible process.
never decreasing. Wow. And this whole concept is captured really elegantly in what's called the entropy balance relation.
The entropy balance, like an accounting ledger for entropy.
Pretty much. It's a formal way of tracking entropy. It states that the change in a system's total entropy over some time period is equal to the net amount of entropy transferred across its boundary, coming in or going out, plus any entropy that is generated or created within the system itself because of those irreversibilities we talked about.
Okay, so entropy can move across boundaries, and it can be created inside. How does it actually get transferred across a boundary?
Great question. Two main ways, according to the second law. First, heat transfer.
Heat carries entropy. Makes sense. Heat feels disorganized.
Exactly. Heat is disorganized energy transfer at the molecular level, so it inherently carries an entropy with it. If heat flows into your system, the system's entropy increases. If heat flows out, its entropy decreases.
And the amount depends on temperature.
Yes. The amount of entropy transferred by heat is simply the amount of heat transferred, Q, divided by the absolute temperature, T, at the boundary where the heat transfer occurs, Q over T.
Okay. Heat transfer, what's the second way?
Mass flow. If mass enters or leaves your system,
Like fluid flowing through a pipe.
right, that mass carries its own entropy with it, just like it carries energy. So mass flowing in brings entropy in, mass flowing out takes entropy out. Its contribution is just the mass flow rate times the specific entropy of the fluid.
Okay, so heat transfer and mass flow bring entropy across boundaries. What about work? Does work transfer entropy?
And here's a really crucial, profound distinction from the second law. Work is entropy-free.
Wow. Okay, say that again. Work is entropy-free.
Work transfer does not involve entropy transfer. Think about raising a weight with a pulley. It's organized energy transfer. Unlike heat, it doesn't inherently increase the disorder or randomness in the same way.
So that's why work is considered a more valuable or high-grade form of energy than heat, because it doesn't carry this baggage of entropy.
Precisely. It's pure energy transfer in that sense. It allows us to perform tasks without inherently increasing disorder during the transfer itself. Now, the process generating the work might create entropy internally.
Right, like friction in the machine doing the work.
Exactly. That's the entropy generation term in the balance equation. That S-gen term is always positive for any real irreversible process. It represents the entropy created within the system due to friction, mixing, heat transfer across a finite temperature difference, all those real-world imperfections.
And for a perfectly ideal reversible process.
For that theoretical ideal, the entropy generation is exactly zero. No new entropy is created. That's the limit of perfection.
Okay, this is fascinating stuff. Let's bring this theory back down to earth, something really tangible. Compressed air.
Ah, yes. The fourth utility.
Right. In factories, workshops, it's everywhere, right after electricity, water, natural gas. And our source dives into this, highlighting just how much wasted energy and wasted money is tied up in these compressed air systems.
It's so true. It often gets overlooked, maybe because air itself feels free. But the energy cost to compress that air, that's definitely not free. Running a compressor for a year can easily cost more in electricity than the compressor itself costs to buy.
Wow.
But the good news, as the source points out, is that there are often simple, relatively low-cost things you can do to save significant amounts of energy and money. Real, practical applications of these thermodynamic principles.
Okay, so our deep dive highlights 4 key strategies. Let's break those down for everyone listening. First up, and this one seems almost shockingly simple, but hugely impactful, repairing air leaks.
Yes. This is consistently found to be the single biggest cause of energy waste in compressed air systems. It's estimated that leaks can count for like 20 to 40% of compressors' output.
40%, just leaking away.
Just silently hissing away into the atmosphere. You pay all that money for electricity to compress the air, and then a huge chunk of it just escapes.
Where do these leaks usually happen?
Oh, all over. Joints, fittings, connections, hoses, valves. Things vibrate, temperatures cycle up and down, seals wear out. Pretty common. I mean, I've seen facilities optimizing huge, complex processes down to the last decimal point.
Mm-hmm.
And then you walk around and hear air just screaming out of a loose fitting. They're literally blowing hundreds, maybe thousands of dollars a year into thin air through a simple leak they could fix in minutes.
It's like finding money in the couch cushions, but on an industrial scale. And the fixes you're saying are often simple.
Often very simple. Tightening a connection, replacing a worn gasket or O-ring, swapping out a cracked hose. You can often just listen for larger leaks. For smaller ones, soapy waterworks look for bubbles. Or you can get ultrasonic acoustic detectors that pinpoint the high-frequency sound leaks make.
And the energy saving is directly related to the energy used to compress that leaked air in the first place.
Exactly. The source gives a great example. Just a single leak, maybe 3 millimeters in diameter, like a small nail hole, on a line running at a pretty standard industrial pressure, say 700 kilopascals, or about 100 psi gauge. Fixing just that one small leak could save a facility around $913 per year in electricity costs.
Over $900 for one tiny hole.
It adds up incredibly fast when you consider most plants have multiple leaks. It's often the lowest hanging fruit for energy savings.
Okay, number 2 strategy, installing high-efficiency motors.
Right. Most industrial compressors are driven by electric motors. And just like any electric appliance, motors aren't 100% efficient. Some electricity gets lost as heat.
So a more efficient motor uses less electricity for the same amount of compressed air output.
Precisely. A higher efficiency rating means less waste heat, more shaft power delivered to the compressor for every kilowatt hour you pay for. So this one makes a good point. Even a 100 kilowatt motor that's 90% efficient.
Which sounds pretty good, 90%.
Right, sounds good. But that still means 10% is lost as heat. That's 10 kilowatts of heat. It's like having a 10 kilowatt electric resistance heater running constantly.
Wow. That's a lot of heat, often just dumped into the compressor room, right? Making it hotter.
Often, yeah, unless it's properly vented. And that heat can then make the compressor work harder, which we'll get to. Another key point here is part load efficiency.
Ah, because compressors don't always run flat out.
Exactly. Many compressors vary their output, and motor efficiency usually drops off significantly when they're running at, say, half load or quarter load. So if your compressor spends a lot of time running at partial capacity, you need to look at the motor's efficiency curve, not just its peak efficiency.
And oversizing the motor is a bad idea.
Yeah, that's a common mistake. Putting in a bigger motor than needed means it spends more time operating in its less efficient part load range. Right sizing is key.
Okay, strategy number 3. This one seems like a clever thermodynamic hack, using outside air for compressor intake.
Yes, this relates directly back to what we said about keeping the specific volume low. Remember, lower temperature means lower specific volume, which means less work to compress.
So instead of drawing air from inside the factory or workshop,
You run an intake duct, so the compressor draws in cooler air from outside the building. Inside air, especially near machinery or heaters, is almost always warmer and therefore less dense than the outside air.
makes sense. Less dense air takes more work to compress to a certain pressure.
Exactly. The rule of thumb here is pretty powerful. For every 3 degrees Celsius drop in the inlet air temperature,
Yeah.
compressor power consumption decreases by about 1%.
1% for every 3 degrees C. That sounds like easy money, especially in cooler climates or seasons.
It really is. Simple ducting can lead to continuous energy savings just by not paying to compress pre-warmed, less dense air from inside your facility.
Simple but effective.
Okay.
And the 4th key strategy, reducing the air pressure setting.
This one is about matching supply to demand. Are you actually running your compressor at a higher pressure than your tools and equipment really need?
Like setting the thermostat higher than necessary.
Kind of, yeah. It takes significantly more energy to compress air to, say, 900 kilopascals, about 130 psi, if your tools only really require 700 kPa and 100 psi. Every extra bit of pressure costs energy.
So check the requirements of the equipment using the air.
Right. Find the minimum pressure required by the equipment that needs the highest pressure, and then set your compressor's control system just slightly above that, allowing for any pressure drops in the piping. Don't just set it to the compressor's maximum rating by default.
And the savings?
Can be substantial. The source gives an example where reducing the plant air pressure from 900 kPa gauge down to 800 kPa resulted in an annual savings of $720 for that facility.
Just by adjusting a setting. Zero cost.
Exactly. Immediate savings, zero capital investment, just understanding the system's actual needs.
Those are 4 great points. Leaks, motor efficiency, inlet air temp, and pressure setting. Anything else major from the source on saving compressed air costs?
Yeah, a couple of other important ones. One is simply turning compressors off when they're not needed, like during nights or weekends if production stops.
They still use power even if no air is being used.
Oh, yes, especially screw-type compressors. Some can consume up to 85% of their full load power, even when they're just idling, not actively compressing. It's like leaving a massive engine running just in case.
85% while idling. That's crazy.
It is. So proper shutdown procedures are vital. And another big one is waste heat recovery. Compressors generate a lot of heat, as we discussed with motor inefficiency, but also just from the act of compression itself.
Right, that heat we want to remove with intercooling.
Well, instead of just dumping that heat into the atmosphere, you can often recover it and use it for something useful, like space heating in the winter, or preheating boiler feed water, or process water.
Turning waste into a resource.
Exactly. It can be a huge energy saver, displacing fuel you'd otherwise burn for heating.
Okay, so wrapping this all up, we started way up high with theoretical concepts like reversible work and entropy.
Yeah, the abstract stuff.
But this deep dive really shows how those concepts have incredibly profound, practical dollars and cents implications. right down to fixing a tiny air leak.
Absolutely. From understanding why steam plants work the way they do because of specific volume, to realizing the surprising cost of that hissing sound from a loose connection. It all ties back to these fundamental thermodynamic principles. Entropy analysis isn't just for academics, it's a toolkit for real-world efficiency.
And if you connect it all, that bigger picture really emerges, doesn't it?
It really does. It highlights that fundamental truth.
Yeah.
Irreversibilities, friction, leaks, heat flowing across big temperature gaps, unnecessary pressure drops. They all generate entropy, and they always degrade performance. They cost you energy. They cost you money.
So every time you find one of those irreversibilities and reduce it,
You're optimizing the system. You're moving it slightly closer to that unattainable ideal, and you're saving resources in the process. It's this constant battle against entropy generation.
which really leads to a final question for you, the listener, to think about. We talked about industrial systems, compressors, but where else? Where else in your daily life or in the systems you interact with your car, your home heating, cooking, anything, can you spot similar opportunities? Opportunities to minimize those inefficiencies, reduce that entropy generation, and maybe get closer to a more ideal performance.
The principles really are universal.
They are. So keep digging, keep asking those questions, keep learning, and we'll catch you on the next deep dive.